Good morning. It's Friday, September the 20th, and I'd like to take a few minutes and walk you through Chapter 4. We'll use Healey, as we always do, primarily as our reference, mainly because he is in more ways than one, he is your study buddy. When you sit down to think about stats and to do your homework, it's Healey who is at your side. Hopefully these videos will be of some help to you, and you can always call me anytime between 5 in the morning and 9 o'clock at night. I check my iPhone, and if I have a message on my office phone or an email, I'll return it within 2 hours. So you're always in touch with me in that sense, so I can be your study buddy as well if you get into a jam. But it's good to follow Healey, I think, for a couple of reasons. One is I think he does very good illustrations of the topics that are covered in each chapter. If you his figures, his tables, if you'll notice in here, for example, he's got one step at a time tables, which are how to do each kind of calculation of the chapter, and walks you through it one step at a time. And then also he has in each chapter not only those, but some I'll find one here in a minute. Applications, like application 4.1 on page 100, where he's actually solved a problem for you and walked you not only in terms of what the problem is, the nature of it, what is it, the question that's being asked. This one in particular is about number of aggressive acts committed by students, and then shows how to do the problem, solves the problem there. You can see the steps. So with his one step at a time, and then his illustrations with the applications, and then a number of demonstrations in the body of the text of the chapter itself, I think it makes him a very good study buddy. And then the other thing is, I get good comments. Well, I don't, he does, on the text. Well, I did get some comments. It's good text, Blanchard. But at the end of the semester, at the course evaluation, I usually get 1 or 2 or 3 or maybe as many as a half a dozen comments on how well people liked Healey and how helpful he was. I don't think I've ever, in all the years I've used him, this is probably the, 6th year maybe, I've never received any negative comments on him. This may be the first semester, so we'll see. Anyway, let's take a look at Chapter 4. Now, one way to think about Chapter 4 is in context of Chapter 3. If you remember, one of the things we were doing in Chapter 3 is looking at the central tendency of a distribution, where this is the low value and this is the high value, and we're looking for a place in the center of the distribution that in one single value captures that central tendency. Think of it as a teeter-totter, and where you've got large values on the left and small values large values on the right, actually, and small values on the left. I'm having to do this like I'm in a mirror. I'm thinking about you where we're looking at this. Maybe I should put it on the board here, where we've got low and high, where we're looking for the center of this distribution. There could be any number of values in here, 1, 3, 7, 8, whatever they are. But what we're looking for with central tendency is, where is the center of this distribution? How can we compress it down to the center? Kind of like the pivot point of a teeter-totter, where we have the low values on the left and the high values on the right, centered. And we saw with Chapter 3 that for continuous variables, for categorical variables, it's usually things like proportions and percentages. But for and a mode, whichever one, like if there are more men in a class, then that would be the mode. But really just thinking about central tendency and continuous variables here, we realize then that we have the mean and we have the median. And the median is the geographical center of the distribution, if you will recall. It doesn't matter no matter, as long as the same number in the distribution remain the same, if this suddenly were 80, the median would stay the same because it's in the geographic center of the distribution. On the other hand, the mean would be pulled to the right. And you remember positive skews and negative skews and that sort of thing. The mean is influenced by the values and the tails. An extremely low value or extremely high value, extremely low value will pull it to the left, extremely high value will pull it to the right. And in the center, no matter what happens there, the median remains geographically centered. So these are the two, in continuous variables, the two best descriptors of central tendency. Now, if you'll recall also, one of the things that we were doing in Chapter 3, unsuccessfully in a sense, we successfully demonstrated that we couldn't be successful at it, if you know what I mean. And maybe you do, and then again, maybe you don't. You remember that we had a set of values. A good way to look at this, rather than put it on the board, because then you'll have it, although you'd have it in the video. If you look in Chapter 3, you'll see that one of the questions that we have once that we have done the central tendency and all, and when we do the central tendency, we collapse it to the center, and all of those other values in the distribution are lost by the collapsing. Everything that was, whatever the individual values were here, they've been submerged into the mean. And so then the question became, well, how do we take into account all the variation around the mean? Between all the variables on the left and all the variables on the right, and the variables between one another and around the mean, all of that. How do we do that? And if you'll notice on the bottom of page 69, review yourself here, table 3.6, if we simply subtract the mean from all of the values, we'll end up with a 0. If we subtract the mean from the high values, we get positive values. If we subtract the mean from the low values, we get negative values. If we put them in a column and add up the positive and the negative, we get a 0. Negative, that balances out that way. So the solution was to square those values and get a whole number that we could sum. And that thing that we were doing then is the numerator and in the formula for Chapter 4 in getting the variance and getting to the standard deviation. So I just wanted to refresh that with you for a moment. So now when we're talking about Chapter 4, we're talking about measures of dispersion and diversity and variability. Now we still hold in place the mean or the median, the mean, let's say, and then what we want to do is we want to, with Chapter 4, begin to quantify the variation that's going on around the mean, all the way out to the low value on the left and the high value on the right. All of those and all those values in between. Summing up all of that variation between one value and another, one value at one end and one value at the other end, between all of them. You can just imagine all of the possible variabilities there are between all the variables within a distribution. How do we sum that? And that's what the variance and the standard deviation is about. And we'll see that the standard deviation is a very powerful tool for us. It is as powerful in dispersion of continuous variables as is the mean and mean in the central tendency of continuous variables. You'll see how that works here in a second. So here, these are the 1, 2, 3, 4, 5 statistics that we want to learn about here in Chapter 4. The index of qualitative variation is the only one of these, really, is the only one of these that applies to qualitative. And there's a good illustration of it here on page 88 and 89 and on over to page 90. It is it's a technique that can be used for measuring, say, and they do here, race and ethnic diversity. Race and ethnicity, of course, is a nominal variable. So what would be of the total population? What's the proportional distribution of that total population across, say, the categories of non-Hispanic white, and African American, let's say. So this allows you to do that, and you can see as you work your way through that those 2 or 3 pages, that the index, the more diverse we are, the higher the value is to 1. It ranges between 0 and 1. And you can see on page 90, I'm not going to ask you in a homework or even on an exam to calculate this, but I will ask you, likely, what would be the qualitative, or should say, what would be the dispersion statistic if we were to have categorical variables? You'd want to speak to this. And if I were to say, if we had 2 years of this and one, the IQV was 0.80 and the other one was 0.20, which one is more diverse? You'd want to know that. And if you look at page 90, you can see how that's played out without having to do the math. Healey's done it for you. You can see in those 3 years from the previous table, page 89, we're looking at 2000, 2025, and 2050 across those 5 or so categories of race and ethnicity. And you can eyeball this in a way. If you look at that table 4.1, we're predominantly non-Hispanic white in 2000. But when we get to 2050, still the majority in percentage is non-Hispanic white, but Hispanic has grown in magnitude, and but the others have remained pretty much the same. African American, Native American, there's been some growth, doubling of Asian American. So we've become more diverse. So if you look at the demonstration of this on page 90, you can see that in 2010, the value of this IQV is 0.58. The next value is 0.72, indicating that we're somewhat more diverse than we were in 2010. And then you've got 0.80 in 2050, where that suggests we're very diverse. And of course, to be absolutely diverse would be probably virtually impossible, but who knows? That would be where each one of these categories has the same percentage. There's 5 categories here, so we'd all be 20%. It's possible that'll happen, but not likely. So anyway, we can see that it's projected in 2050 that we'll be highly diverse because the IQV will be 0.80, and that's how you would use this. So know what it is and know what the values mean. If you've got a high value relative to a low value, then you know the high value is going to be more diverse than the low value and all of that. Now, let's back up a page and take a look at the figure on page 4.1, holding the text up here. I don't know if you can see this. Take a look at this. What you have here are 2 normal curves, and these will be the subject of chapter 5. But they give us an interesting visual impression, or description, I guess, or image, of dispersion. If we were to, in a situation we had to make a decision which one of these 2 ambulance companies to call to come to our aid, if we had this image in front of us, which one do you think you would do? Which one would you call? I'll give you a second to contemplate that, since you've read this chapter, I'm sure. Well, I tell you, what you would do, you can see here that the minutes are 0 to 14 in the x-axis in both cases, and the frequency is 0 up to 200 and something or more in the other. So if we look at this, we can see that inside this bell curve on the top that is more steeped, we've got 0 to 14, and here's the mean. This is another one of those. Here, this is telling you an illustration here where the means are exactly the same. Both of these have the same average amount of response time, 7 minutes, I think, something like that. So this is a 7 and this is a 7. But what's different about this is how much variation there is. If we've got this is about 4 here, and this is about 10. So this would be about 4 here, and this would be about 10. If we look at these, we would say, while they both are on average the same in their response time, one is a little more, shall we say, dependable in estimating when it'll arrive. The variation here, the range, if you will, between 4 and 10 is pretty good. You know, they may get here less than 4 minutes, or they may get here longer, but they're coming pretty much between 4 and 10 minutes with an average of 7. If we do this, you can see that this one, the curve is all the way out here. So there we would say, while the average is 7, it could be anywhere from 0 minutes to 14 minutes, somewhat less dependable. On average the same, but the variability in the response of B is much greater than the variability in response of A. So I think if we had to choose, we'd choose A, because the variability in the response time is less and consequently more dependable. So that's a good illustration of, in concept, and of what what we're doing in this chapter. All right, let's look at the range and the interquartile range. The range and the interquartile range. Let's take the range first. It is the low. The range is the high value minus the low value. If we had something that was 1, 3, 7, 9, and 15, and 1, 4, 8, 11, and 22, if this was A and this was B, here's the low value of these two, and these are the high value. If I subtract 1 from 15, the range is 14. If I subtract 1 from 22, the range is 21. So we'd say, using the range, that there's probably greater diversity. Well, there is greater diversity. There's a much greater range between the low and high value in B than there is in A. So we could say, that's cool. We got something about diversity that is that we can say one has a greater range than the other. The other point to make here, as an aside, is statistics really work when you've got two or more distributions. I mean, there are some statistics we'll see where if you just have one distribution, that's cool, you can really understand some stuff. But things like this, if I just said the range of this was 14, we wouldn't know whether that's large or small relative to something else. So we need to have that something else, like another distribution or more distributions, to make some comparisons. And that's true for a lot of stuff we're talking about in this chapter, and for a lot of stuff that we're talking about in all the chapters of the text. All right, now the interquartile range, I'm just going to call it this. The interquartile range is kind of an interesting thing. Here we've got a low, let's just say 2, 3, 5, 6, 7, 8, 10, 11, how many is that? 1, 2, 3, 4, 5, 6, 7, 8, 12, and then down here I'm going to put a 1 again, low. So I can get 10 out there. If we this is the high right here, 12. Interquartile range. So what we're trying to do here, we know that if we were just to get the regular range, we'd subtract 1 from 12 and we'd say the range is 11. But what we're trying to do with this one, let's just make a real large value here, 63. So the range there would be 62. One of the things we want to do with the interquartile range is take into account the either relatively low values on the left or the high values on the right that are skewing it. Remember, if we have high values, it skews to the right. If we have low values, we get a negative skew to the left. The interquartile range is taking the middle 50% of a distribution, with the idea that if we eliminate the 25% to the left and the 25% to the right, then we have that middle 50%, and we get a better image of the natural internal distribution of that without being unduly influenced with extremely low values on the left or extremely low values on the right. So the way you would do this is 10 right here. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10 values. You would if you would take, in order to get that 25%, you go 10 times 0.25, which would be 2.5. Let's just round it up to 3, just for demonstration here. So there, right there, is the beginning of the end of the first quartile, and we could go 3 this way. 1, 2, 3. So there is 25% up here, 25% up here, and here in the middle is in the middle 50%. And then we can look at this. And then if we were to look at doing comparisons between two or more distributions, by eliminating the low values and the high values, then maybe we get a little better comparison of what the internal distribution of that dynamic of that distribution is without regard to the low and high values. But there again, like in the range, when we do the range, we've got a low value and a high value, but we completely disregard everything in the middle. We do not yet get our minds around all that diversity around the mean. We're just looking at the difference between the low value and the high value. And then so the interquartile range, it's a cool procedure, and it's very commonly used, like the range in statistics. But here again, we're missing something. We're intentionally losing something. We're dropping out. We're eliminating the values in the bottom 25% and the values in the top 25%. Now that leaves us the middle 50%, and that's good for comparison purposes, but we've lost information in the left tail and in the right tail. So the interquartile range is particularly good to use when you've got some unusual outliers. Outliers are those things that pull the tail one way or the other. Those are called outliers. So when you've got a distribution with unusual outliers, it's good to do the interquartile range comparison between two or more distributions, because you get a better opportunity for comparing that internal dynamic uninfluenced by the outliers. But we lose information. 50% of the information we've intentionally eliminated from the distribution. So it's good, but it's not really the best. All right. So if we erase. That's kind of eliminating, isn't it? This one. Then where we want to be now is the variance. And this is well discussed and laid out when you get on to about page 93. By the way, you'll find one step at a time tables or boxes for each of these ranges and interquartile range and IQV and all that we've just talked about. When you get over on pages 94 and 95, we're getting into the variance. Now, when we this one, the variance, is the sum of xi over minus x bar over n. Now we look at this and we say this is familiar. This is what we did at the end of chapter 3 to try and get our minds around how can we capture the variance around the mean. If we simply subtracted the x bar from the xi, where we had the pluses at the top and the zeros and the minuses here, and then we added those up, we got a big zero. We saw how that was. So we squared it, and then we got this numerator, basically. That's the same thing we saw at the end of chapter 3. But now what we're doing is we're taking that piece of the formula and dividing it by the number. The n equals the number of values in the distribution. So if you've got 8 values in your distribution, you divide it by 8. If you got 153, you divide it by whatever you got here by 153. Now, let's put the standard deviation. The variance is something we use in statistics quite a bit, but what we really use is the standard deviation. And so let's go after that one. And then you're going to see this is kind of peculiar in a way. Mean squared. It's exactly the same formula here, except we're going to take the square root of that. We're going to do this first and then take the square root of that. And that's why you have this peculiarity of why of this being squared. If you have a square here, notation with a value, you think, well, something else has already happened, and then you square it. So what's really happening here is this, and then you take the square root of that. Another way of capturing this in a way, I think maybe you can, let me put it in red. Another way of thinking about the relationship between these two is, well, first off, let's say that this is the variance. The variance equals this. Now we know it's s squared, and then the standard deviation equals this one. So another way of thinking about how this works, kind of an easier notation, is that the standard deviation equals the square root of the variance. You do the variance, and then you take the square root of that to get the standard deviation. So maybe this will help the notation and make more sense than the more formal notation that's used in statistics. Okay, so let's take a look at some illustrations rather than do a lot of stuff on the board. Kind of walk our way through the chapter here. and see what we can find out about this standard deviation and why it's so important. There you can see at the bottom of page 95 that, like so many things in statistics, it requires an extension table. And extension, I mean by that, if you look at table 0.44, you've got a column of xi, and then you've got to build a column for deviations, and then you've got to extend farther out to the right, deviation squared. There are some tables that we'll encounter this semester that might take you out 4, 5, 6 columns. Kind of like the table that we did when we were looking at frequencies of when we were calculating out the intervals and the frequencies, and we did the intervals and then the frequencies and then percentage of the frequencies and the cumulative percentages of the frequency, and et cetera, et cetera, et cetera. That was in chapter 2. That was an extension table. Extension tables are often the foundational way, ledgers, if you will, for putting this data together so that we can kind of begin to calculate with it. Put it in an order that's useful for us. There again on page 96 you can see a one-step-at-a-time box, how to do the variance. And there you see an illustration. But let's look at that 4.6, computing the standard deviation. Here we've got a residential campus and an urban campus. And the idea is, what is the variability of age? We might guess, and historically it's been kind of the case, although not quite so much anymore, that the residential campus of students are the younger students who come and live in the dorms, and the urban campus, or the commuter campus, shall we say, are often older people who work during the day and they come to the campus on the weekend or on the evenings to go to school. So we might guess that the urban campus is a little bit older than the residential campus. But let's see how this plays out. There you can see two extension tables on the page on page 97. Fortunately for us to eyeball this, it's a very small group of people, right? I think it's 1, 2, 3, 5 in each group, so we can see the distinctive differences between them. And there you can see the extension table of residential campus going out across the deviations, and we see that it sums to 0. Have we demonstrated that to ourselves before? Yes, we have. And so we square it. And you come over on the right-hand side and then sum all that up, and you can see there that the sum of xi minus x bar squared is a 4. That's the top of our variance formula. And there you can see that they also calculated out the mean of 19 in order to do that middle column. Okay, so then we go down to the next extension table and we do the same thing. That's the urban campus, and you can see there the numerator is 88, a hint already that we might have a good deal more variability in the evening one than in that numerator that we have in the first one, which is only 4. And there again we can see the mean for the residential campus is 19 years of age, and the mean for the urban campus is 23 years of age. So we can see there's some older people, perhaps older population in the urban campus. Now if you go back to the net page to 96 at the bottom, you can see the formula where they've done the variance and then taken the square root of that and get a standard deviation of 0.89 for the residential and a standard deviation of 0.429 or 420 for the urban campus. Now, the important thing about the standard deviation, which they'll talk about here in a minute, is over in the latter part of the chapter. It's an index of variability. So if you've got two values, two distributions, and one has a larger standard deviation than the other, that automatically tells you that the one that has the larger has a more broad distribution, perhaps a wider range, if you will. And if we go back to the first part of the chapter where the shape is, a more rounded shape than the heap shaped of a standard deviation that is smaller. So if we saw these two, if we were to visualize the shapes of these two distributions, 0.89 would be more like ambulance A, and urban campus would be more like the company ambulance B, rounded and flatter. So standard deviation is just looking at the numbers without even looking at anything else, but you just have the standard deviation. You automatically know that one is broader, more diverse than the other. And we can confirm that by looking at these numbers. If you look at the ages, the difference, the low value is 18, the high is 20, a range of 2. If you look at the ages for the urban campus, the lowest value is 18 and the highest value is 30, a range of 12. So there are all kinds of indications that suggest to us the range and the variance and the standard deviation, that the urban campus is far more variable in age than is the residential campus. And we can imagine what that shape will looks like, sort of modeling it after what we saw for the ambulance demonstrations at the beginning of the chapter. And we'll see when we go to chapter 5, it's all about these shapes. All right, let's keep going down through here and see if we can find, disregard section 4.7, computing the standard deviation from group data. We will not do that at all, not at all. Let's go to 4.8, interpreting the standard deviation. You can see that they have 3 reasons why it's an important thing. 2 of them sound the same to me. I think the thing that's most important about those 3 to remember in terms of concept, that the standard deviation is an index of variability, as they say here, an index of dispersion, an index of diversity. We would say that the age group of the urban campus is more diverse than is the age range or the age distribution of the residential campus. It's less diverse. The residential campus is less diverse, it's less variable, it's less dispersed. The urban campus is more variable, it's more diverse, it's more dispersed. So when you've got 2 or more, which is again what you need in statistics really to get some good sense of what's happening here, you can see that the index of or the standard deviation is an index of variability. If you've got an array of standard deviations, you can quickly see, lay them out from low value on the left to high value on the right, and the one out on the far right or the one out on the right is going to be the most variable, the most diverse, and the one on the left is going to be the least diverse, the least variable, and all those in between are going to be somewhat in between. All right, so I think let's look at one more illustration here. And that would be on page 101. Here we're looking at traffic fatalities in the eastern states and traffic fatalities in a selection of western states. And we've got 2 extension tables here again. In the eastern states, you can see it's Pennsylvania, New York, New Jersey, Connecticut, Massachusetts. There you can see the sum. You can see how they're doing the extension tables. You can see the sum of xi minus x bar squared is 30.40, and you drop down a little ways and you can see that the mean for the eastern states is 12.92 fatalities per 100,000. And there you go down a little bit farther and you can see that the standard deviation is 2.63. Now those are interesting values, but they don't really tell us anything unless we have something to compare it against. Well, let's go to the western states and see what we got. Wyoming, Nevada, California, Oregon, and Washington. There you can see the extension table. It's followed all the way over to the right, and you can see the sum of xi minus x squared, x bar squared. They left the bar off that particular one, but that's okay. Is 612.36. One is 34 in the east, the other one is 612, so we're getting a hint of a lot of variability. So the mean for the east was 12. We look at the mean for the west, it's 23, almost twice as much. So we see that the higher number of there are a lot of higher number rates of fatality going on in the west. Again, the mean and the median are very quick without knowing anything else. If you've got the mean of 2 distributions, you know that one is greater than the other, and you can begin to imagine what all that is, even without the data to back it up or behind it. And then you go down to the next table, or down the formula for standard deviation, you see a standard deviation of 11.06. So we can see on average the rate is higher, but we can also see in terms of fatalities per 100,000, but now we can see a lot more variability. So let's take a look at the distribution. Pennsylvania varies between about 10.25 and 17.67, that's the range. We look at the western states, it varies between 11.01 and 43.16. That's a considerable range. You can, I guess the mean would be just about Nevada and obviously pulled to the right. You can see if we lay that distribution on the horizontal, the mean is pulled towards Wyoming. And here we look at the mean in the east, 12.92. It's about in the center. About New Jersey to New York. So the mean is just slightly pulled to the right, but not near as skewed to the right in a positive skew as is Wyoming does to the western states. So we can see from the distribution that there is considerable variability in the west. Probably want to stay away from Wyoming. And much less diversity in the east. So that's the story of dispersion. And hopefully with a little comparison of the central tendencies of threes, it's making sense. Your homework is out there. It's due Tuesday. So go ahead and work on your homework. And if you please be sure to send it to me in a regular Lake email. Don't post it on Blackboard, even at this moment. I'm still struggling to finish the homeworks 2 and 3 that have been posted, 3 particularly, that was posted on Blackboard. I'm actually going to have to come in on Saturday, tomorrow, and finish that out. I'm not complaining. But I'm hope that if you send it to me by email, which will begin next week, then I can get into a rhythm where I can get these graded quicker and turned around to you with grades much quicker than I am right now. So I apologize for the delay. Anyway, that's our Friday video and Chapter 4. And call me, email me if you get into a snag on any of this homework, and I'll be back to you anytime between 5 and 9 o'clock, 7 days a week, and I'll be back to you within 2 hours. So, there's a weekend coming up, and you be careful out there, and talk to you next week.